Hello everyone, this is Kalpana here. In this video, we are going to see a problem from partial differential equations. So let's get going. Problem: find the partial differential equation by eliminating the arbitrary constants a, b from the equation x minus a whole square plus y minus b whole square equal to z square cot square alpha. So here are the useful notations we always need to remember while solving a partial differential equation. While solving a problem from partial differential equations. Okay. We are given a relation or an equation x minus a whole square plus y minus b whole square equal to z square cot square alpha, right? It has constants alpha, ab, arbitrary constants ab, and here alpha is a constant. We'll consider cot square alpha as a constant, right? Now consider this equation as equation 1. Now partially differentiating 1 with respect to x. That is, we will differentiate equation 1 on both sides with respect to x. Okay. Since we are partially differentiating with respect to x, so we'll treat y as constant, and here z is a function of x and y. Okay. Y will be treated as constant. So we'll write this as plus partial derivative of the second term. In second term we don't have any x, right? Y and b are considered as constants, and here cos square alpha is considered as constant, so we'll write it as cot, okay, cot square alpha into partial derivative of z square with respect to x. So now partial derivative of x minus a whole square with respect to x will be 2 times x minus a into the inner derivative, that is partial derivative of x minus a. Plus partial derivative of a constant with respect to x is 0 equal to constant into partial derivative of z square with respect to x is 2z into partial derivative of z with respect to x. This gives us 2 times x minus a into partial derivative of x with respect to x is, or you can write this as okay, equal to cot square alpha into 2z. We have a notation, dou z by dou x is p, so we'll replace it by p, right? And this gives us 2 times x minus a into partial derivative of x with respect to x is 1 minus partial derivative of a constant with respect to x is 0 equal to 2zp cot square alpha. This gives us 2 times x minus a into 1 minus 0 is 1 equal to 2zp cot square alpha. Now we can write this as 2 times x minus a equal to 2zp cot square alpha. Now take this 2 to RHS, you'll get x minus a equal to 2zp cot square alpha by 2, where 2 gets cancelled, and you'll get x minus a equal to zp cot square alpha. Consider it as equation 2. So you got equation 2 now. This is x minus a equal to zp cot square alpha, right? Now by partially differentiating 1 with respect to y, we'll get another equation. So let's see that. Partially differentiating 1 with respect to y. See here, z is a function of x and y. Okay, here we are partially differentiating with respect to y. So we'll treat x as constant. Here x minus a whole square is constant, and in this cot square alpha is constant. Okay, now we'll write this as dou by dou y of constant plus dou by dou y of y minus b whole square, where b is constant, equal to constant cot square alpha into partial derivative of z square. Okay, this gives us partial derivative of constant with respect to with respect to y is 0 plus partial derivative of y minus b whole square with respect to y is 2 times y minus b into inner derivative, that is partial derivative of y minus b equal to cot square alpha into partial derivative of z square with respect to y is 2z into dou z by dou y. This gives us 2 times y minus b into partial derivative of y with respect to y minus partial derivative of a constant b with respect to y equal to cot square alpha into 2z. We have a notation dou z by dou y equal to q. So we'll just replace it with q. Now we'll get partial derivative of y with respect to y is 1 minus partial derivative of a constant with respect to y is 0 equal to 2zq cot square alpha. Okay, from this we'll get 2 into y minus b into 1 equal to 2zq cot square alpha. Right, we can cancel this too. Then you'll get y minus b equal to zq cot square alpha. Now consider it as equation number 3. Got y minus b equal to zq cot square alpha, which is our equation 3. Now observe equation 1, 2 and 3. See, in equation 1 we are having x minus a where a is a constant and y minus b where b is a constant, right? So we have to eliminate, since we have to eliminate constants a and b from this equation to find the partial differential equation, right? So by eliminating x minus a, by replacing x minus a by zp cot square alpha using 2 and by replacing y minus b by z cube cot square alpha by equation 3, the constants, arbitrary constants a, b gets eliminated. Finally, from that you'll get the required partial differential equation. Okay, and if you notice here I have did every step in order to show you. Okay, but you can just skip these steps. Okay, you can just skip steps and you can just directly write this too. Okay, it is not necessary to write these 4 steps. Okay, fine, we'll see the direct method also. Now coming to the problem. Now we have to observe 1, 2 and 3. Okay, by observing we came to know that x minus a and y minus b can be replaced by some terms which does not has any arbitrary constants. Okay, so now we'll substitute 2, 3 in equation 1. We get, already we have equation 1, which is x minus a whole square plus y minus b whole square equal to z square cot square alpha, right? Now substitute 2 and 3 in 1. We get just replace x minus a by zp cot square alpha, you'll get zp cot square alpha whole square, plus replace y minus b by zq cot square alpha, you'll get zq cot square alpha whole square equal to z square cot square alpha. Since x minus a equal to zp cot square alpha and y minus b equal to zq cot square alpha by 2 and 3, right? And this gives us z square p square cot power 4 alpha plus z square q square 2 2s are 4 cot power 4 alpha equal to z square cot square alpha, right? If you notice, we are having cot square alpha in RHS and cot power 4 alpha in LHS. So let's take cot square alpha common from these two terms, then you'll get cot square alpha into z square p square. Otherwise we can just take z square cot square alpha common. Okay, fine. Now let's take cot square alpha common and let's see what happens. So z square q square cot square alpha equal to z square cot square alpha. What happens if you take z square cot square alpha? Just z square cot square alpha gets cancelled from the LHS and RHS. So let's take z square also. Okay, let's finish it in one step. Done. Now take this z square cot square alpha to RHS, otherwise cancel it here itself. We'll get p square cot square alpha plus q square cot square alpha equal to z square cot square alpha by z square cot square alpha, which gives us 1, right? Then p square cot square alpha plus q square cot square alpha equal to 1, right? Now take cot square alpha from these two terms, we'll get cot square alpha into p square plus q square. P square plus q square equal to 1, right? Now take this cot square alpha to RHS, you'll get p square plus q square equal to 1 by cot square alpha. Since we know that reciprocal of cot is tan, so reciprocal of cot square alpha will be tan square alpha, right? This gives us p square plus q square equal to tan square alpha, which is the required solution. Therefore, p square plus q square equal to tan square alpha, right? It does not involve any arbitrary constants a and b, and also this of f of x, y, z, p, q equal to 0 form, right? Okay, and it does not involve any constants, so this is a required partial differential equation. This completes the problem. Okay, we have finished the problem. Now we are going to see how we'll partially differentiate 1 with respect to x and y without increasing number of steps. Okay, so firstly I'll partially differentiate with respect to x. Okay, since it is x, y will be treated as constant, and we know that z is a function of x and y, and here cot square alpha is constant. That we have to know, right? Now we'll just partially differentiate 1 with respect to x. Partial derivative of x minus a whole square is 2 times x minus a into partial inner derivative of x minus a, right? Partial derivative of x with respect to x is 1 minus partial derivative of a with respect to, that is constant with respect to x, is 0. So 1 minus 0 is 1. Just write 1 plus partial derivative of a constant. Here y and b both are constants because we are partially differentiating with respect to x, right? So the partial derivative of y minus b is 0 with respect to y, equal to partial, it is a constant, okay, cot square alpha, let it be. Now partial derivative of z square with respect to x is 2z into inner derivative dou z by dou x into cot square alpha, right? Now from this we'll get 2 times x minus a equal to 2z. Just replace it by the notation p. You'll get p into cot square alpha, right? The 2 gets cancelled and you'll get x minus a equal to zp cot square alpha, which we have considered as equation 2. Now partially differentiate 1 with respect to y, okay? So here we need to partially differentiate 1 with respect to y. So x is treated as constant. Here x minus a is treated as constant and alpha, cot square alpha is treated as constant, okay? Now, so you'll get partial derivative of a constant with respect to y is 0 plus partial derivative of y minus b whole square will be 2 times y minus b into inner derivative. Partial derivative of y with respect to y is 1 minus partial derivative of a constant with respect to y is 0. So you'll get 1 minus 0, which is 1, okay, equal to 2z into partial derivative of z square with respect to y. So I'll get 2z into inner derivative dou z by dou y into the constant cot square alpha, right? This gives us 2 times y minus b equal to 2z. Just replace dou z by dou y by the notation q. Okay, now you can cancel the 2. You'll get y minus b equal to zq into cot square alpha, which is considered as 3, right? Now notice the 3 equations, equation 1, equation 2 and equation 3. So from this we'll come to know that if x minus a can be replaced by zb cot square alpha and y minus b can be replaced by zq cot square alpha, the arbitrary constants a, b gets eliminated, right? So we'll just substitute 2 and 3 in 1, okay? We have 1 x minus a whole square plus y minus b whole square equal to z square cot square alpha, right? Now substitute 2 and 3 in 1 or in the above equation and we get zp or z square p square. Let's write it, okay? Cot square alpha whole square plus zq cot square alpha whole square equal to z square cot square alpha. From this we'll get z square p square cot power 4 alpha plus z square q square cot power 4 alpha equal to z square cot square alpha, right? Now let's take z cot square alpha. See, you're having cot square alpha in RHS and here you're having cot power 4 alpha. So we can take cot square alpha common from these two terms and here you're having z square. In these two terms also you're having z square. So let's take z square cot square alpha common from the two terms of LHS. Then you'll get cot z square cot square alpha into p square cot square alpha plus q square cot square alpha equal to z square cot square alpha. Okay, here itself you can cancel z square cot square alpha or you can take z square cot square alpha to RHS. Okay, and you'll get p square cot square alpha plus q square cot square alpha equal to z square cot square alpha by z square cot square alpha. By cancelling these two, you'll get 1 here. Now take cot square alpha common from this. You'll get cot square alpha into p square plus q square equal to 1, right? Now Take this cot square alpha to RHS, you'll get p square plus q square equal to 1 by cot square alpha. Since 1 by cot square alpha is tan square alpha, so from this you'll get p square plus q square equal to tan square alpha, which is the required partial differential equation. Okay. Well, we have seen a partial differential equation, a problem from partial differential equations in this video. I hope you'll understand. We'll see you in the next video. Until then, bye bye.